So today's lesson is the first lesson in our first course of the grade 9 work, which is whole numbers. Now, in this section, we're going to talk about whole numbers. We're going to talk about integers as well, which I'm going to explain all in a second. But basically, these are like, I don't want to say the most basic of numbers, but these are really the foundation on which our mathematical knowledge is built on. If we can work with these types of numbers in different operations, hopefully that means we'll be pretty confident moving forward. So what I've got here is a little like diagram that explains what the number system is. Now, some of you might have seen something like this before. Some of you might have spoken about this before. But basically the number system, and specifically here, the real number system, are all of the numbers that we have worked with in maths. We do get what we call the non-real number system. I don't want you to stress about that right now because it's not something that's going to come up generally in grade 9, 10, maybe a little bit in grade 11, but it's not a huge thing that we need to stress about. The real number system is the one that we work with the most. Now, the real number system, you can almost imagine like measuring cups. If you have no idea what I'm talking about, I actually should have brought my measuring cups with me. It's those cups that sort of like fit into each other. And so what I mean by that is, and I'll explain this as we go along, is that certain numbers can fall into multiple categories or multiple groups within my guys, let's I'm just going to take a second. Let's just make sure we're all on mute. Otherwise it does become a little bit chaotic. Who knows who it is, but anyways. So our number system, often numbers can fall into multiple groups, which is absolutely fine. But sometimes numbers are quite specific, and you're going to see what this means as we go along. So the first type of numbers that we're going to start with, and we're going to sort of work our way out of this diagram, are natural numbers. So these are the ones in this sort of yellow block over here. Now I'm going to ask, we'll see if anyone can give me an answer. Can anyone tell me, you can raise your hand or you can put it in the chat, what are natural numbers? It doesn't have to be like a perfect definition. What are natural numbers? Kia?
Hi, ma'am.
Hi.
Ma'am, natural numbers are positive counting numbers excluding 0.
Excellent. Okay, so guys, these are, and I like what Kia said there, these are essentially what we call or can call our counting numbers. Now, basically what that means is, think about when you started learning to count, you started with 1, 2, 3, 4, and so you kept going. And so your natural numbers are exactly that. All of the numbers that we learn to count with. I'm not going to write them all out, but basically this can go all the way up to positive infinity. So these are sort of our first group of numbers that we can classify numbers into. There are our counting numbers, 1, 2, 3, 4, 5, etc., etc. Eddie, I see a hand.
Ma'am, they're just like your neutral unchanged numbers, right?
When you say neutral unchanged numbers, can you explain that a little bit more for me?
They're like normal, ma'am.
Yes, yeah. Yes, for lack of a better word, they're just our normal basic numbers, exactly. Okay, now guys, obviously mathematicians always like to have a symbol for something because if they don't have to write it out, that's a bonus. So our natural numbers, and the reason I'm showing you this is because often, because mathematicians are quite lazy, they don't write it out and they just use a symbol. So you need to be familiar with the symbol for each of these types of numbers. Now, natural numbers, I want to say it's like a fancy N. I'm clearly not doing it very well tonight, but is basically an N. I always do it with like a double line in the middle just to show that it is slightly fancier than just your normal N. And if you see just an N for your number system, we're talking about the natural numbers. Okay, so those are your natural numbers. Can anyone tell me, if we move up the blocks, what are whole numbers? Whole numbers are slightly different than natural numbers. So what are our whole numbers? Amahle, do you want to tell us?
Numbers starting from 0 to infinity.
Excellent. Well done. So again, because mathematicians like to complicate things sometimes, we have created a whole new category of numbers to include one more number. And so these are now essentially all of your natural numbers, but now including 0. So 0, 1, 2, 3, 4. You know, mathematicians are brilliant, but sometimes very confusing. So all of those counts.
Complicating things.
I know, right? Why did we need a whole new group? I mean, I get it, 0 is a bit different to the rest, but honestly. Okay, so essentially it is your counting numbers as well as 0. Now again, we've got a symbol for this. It's nothing too groundbreaking because it's basically all of the natural numbers, it's an n, but then we put a little 0 at the bottom to show that we are including 0 in this case. So those are your whole numbers. Now I just want to take you back to this diagram over here because some of these numbers are on a bit of a weird format, but the point that it's trying to show you is that once you simplify something, if you get a whole number, well, that's what it is. So if we look at this fraction over here, 9/3, we know that 9/3 simplifies to 3. 3 is then part of that sequence, 0, 1, 2, 3, and so it is a whole number. We know that the square root of 36 is 6. That is part of the sequence, 1, 2, 3, 4, 5, 6, and so it is a whole number. And so we always need to make sure that when we're trying to classify numbers, and we're going to do some examples in a second, we always make sure that we're working with the simplest version of that number, because sometimes, especially when it comes to like fractions or square roots or decimals, sometimes if we don't simplify it, we can classify or categorize or group that number incorrectly, and we don't want to do that. Right, so those are our whole numbers. So can someone tell me what integers are then? Jabulo, what are integers?
Hi, ma'am.
Hi.
Integers, ma'am, include negative numbers.
Okay, now what are, okay, you're my English there for a second. Do we include fractions with integers, or is it just like the whole numbers?
I think the whole numbers are
Excellent.
fraction. Yeah.
Okay, so guys, here integers are all of your positive and negative whole numbers. So this is now where our negative values start to come into our number system. And you can almost imagine this like your number line. We know that our number line, if we're talking about integers, can start all the way at negative infinity, keep going, then we would get our negatives, so let's say -2, -1, 0, and then we would go into our positives, and we could keep going all the way up to positive infinity. So your integers now start to include the negative whole numbers all the way from negative infinity to positive infinity. So again, if we look at this fraction of 8/2, if we simplify that, that gives me -4. That's an integer. If we think about it on our number line, it would fall there. The square root of 4 is 2. That's an integer. So it is or can be classified as an integer. Can you all see a hand?
I wanted to tell you what rational numbers are.
Ah, on it. Okay, so rational numbers, let us know, Kanyo.
Rational numbers include all natural numbers, whole numbers, and integers.
Excellent. Okay, perfect. So this is now what I'm talking about, the measuring cups. Rational numbers, as you can see, the blue blocky here is including or is also surrounding the integers and the whole numbers and the natural numbers. And so what that means is that natural numbers, whole numbers, and integers are also rational numbers. So rational numbers, and I'm not going to write all of that out, as even though it's perfectly correct. Rational numbers are essentially numbers that can be written as a fraction. That's like a clue or a sign that these are rational numbers. A fraction. Okay, now the reason that is like our indicator for ourselves is because if we think about, let's say, the number 3. 3 is a natural number, 3 is a whole number, 3 is an integer. It's all of those things. But 3 is also a rational number because I can write 3 as a fraction as 3/1. That's still a fraction. We would never write 3 like that, but I can. Something like, let's take the decimal 1,3 recurring. I can write that as a fraction as 0,3 recurring. Sorry, I can write that as a fraction of 1/3. So as long as either the decimal can be written as a fraction or the whole number or the integer can be written as a fraction, as long as we can write the number as a fraction, it is a rational number. So even though we've got 1,5 and 3,78, those can be written, those can be written as fractions. We know that 1.5 as a fraction is 3/2, and 3.78 as a fraction is not a very nice one, but 189/50. So as long as I can write it as a fraction, it is a rational number. Right. Sorry, I didn't have my chat open because I have a lot going on here. Asetu and Naseho, sorry. I can see that you had asked for a repetition of the definition. I'm going to say it again. Just let me know if you need me to say it once more. Rational numbers are numbers that we can write as a fraction. As long as you can write it as a fraction, it is a rational number. Right, guys, just quickly, and I do see some hands, but I've just forgotten to put the symbol for integers. Integers is a Z. Rational numbers is a Q. Can't tell you why it's a Z and a Q. It probably comes from some ancient Roman, Latin, Greek word for those two things, but integers is a Z, rational numbers a Q. Okay, Tando, do you have a question?
Actually, ma'am, it's to answer the definition of irrational numbers.
Okay, give me 2 seconds. I will come back to you. I just want to make sure that the other two aren't questions.
Okay, ma'am.
Kia, do you have a question?
Ma'am, I also wanted to say the irrational definition.
Okay. I'm going to give Tando the chance now, but don't stress. There will be chances of plenty. Okay, Tando, tell us.
So it's any real number that cannot be expressed as the quotient of two integers.
Oh, that is a fire definition. Took my brain a second to understand that. Excellent. Say it again for me. I actually really like that definition. Are you still there? I love that bit of a wild one here. So I'm hoping I'm gonna say what Tandor said correctly here. Oh, there we go. Tandor's gonna help me. Tandor, say it again. That was beautiful.
So, ma'am, any that cannot be expressed as the quotient of two integers.
Fantastic, love it. So guys, just so that we're all clear, quotient is what we get when we divide two values. So basically a fraction. And so essentially what Tandor's saying here is numbers that can't be written as a fraction. Can't. So if you can't write it as a fraction, then it is irrational. And so if we go over to our little pink block here, if you type the square root of 5 on your calculator, which I'll do and show you, your calculate, if it can. Now, if I type the square root of 5 on my calculator gives me back the square root of 5. And so what that means is that it can't be written as a fraction. And so it only has a decimal form. Now that makes sense. If we look at this decimal, there's no pattern to it. There's no numbers repeating. Obviously, your calculator can't go on for infinity, but generally your calculator shows you, what is that, 2, 4, 6, 8, 10 decimals as its maximum. This probably means that it's going. So if there's no pattern into the decimal, we can't write it as a fraction. And so it means that it is an irrational number. Now, irrational numbers symbol is again a Q, but it's got a little apostrophe. Now, this little apostrophe you're going to see quite a bit in math. I don't want you to just say it is not a rational number or some sort of change from an original, but it's a little Q with a dash and now is our irrational numbers. Right, excellent, guys. You did really, really nicely there. I am going to want to take a screenshot of this. I know it is a lot of information, and it's a lot to absorb, but we're going to practice taking a screenshot because I don't really want to. But these are sort of our 5 groups within our real number system. Yes, your hand.
Ma'am, before you screenshot, just to add on what Kanda said, irrational numbers can also be written as decimals that neither recur nor terminate.
Perfect. Okay, so if we want to add to that, I'll be honest, when it comes to the number system, I'm very basic definitions. So here's added here, it is a decimal, can be written as a decimal that doesn't recur, which basically means repeat. So there's no pattern to the decimal, like 3333 or 56565656, such as a random bunch of numbers, or a decimal that never ends. So it goes on for an infinite amount of time. That's not how. So definitely add that on if you would like to. It's a decimal that doesn't recur, so it doesn't, and it generally doesn't end. Eddie, you want to add to?
Ma'am, I'm just trying to suggest that ma'am might have to turn off ma'am's camera because it's lagging a little.
Okay, cool. Thank you. Is anyone else lagging? Can you just let me know in the chat? Or we all fine? I know that network is a... Okay, I'll turn off my camera. Let's see if it helps. You don't really need to see my face, I suppose. Okay. Right, I'm hoping we've all got a screenshot. I'm about to move, so if you don't have a screenshot, do it now. Right, so we're going to practice this, but yeah, let's take a little break because it's hot. Oh, I'm hot, and we're already halfway through, so I'm going to jump down to our brain break. Now, remember, brain break is a chance for you to get up, stretch, make sure you've got the blood flowing to the brain, and I always give you a joke. I always give you then like a little puzzle or a little math sum or something to give it a go. So in this case, our brain break here is a large square. So this is a square that is divided into 4 small, or is divided into smaller squares, I should say. In one of the squares, a diagonal is also drawn. So when we're talking about a diagonal, we are talking about this line over here. So that's the diagonal. Now that's important. I'm not going to tell you why, because you're going to try it. What fraction of the large square is shaded? Now, just so that we're all very, very clear, the large square is then this big square over here. So I want to know from you, what fraction of the large square is shaded? Take a second, think about it. We've already got some answers coming through, which is awesome. Love that we're trying. Even my computer is now shouting at me that my internet connection is unstable. Can't tell you why. We'll figure it out. Right, obviously, if you want to raise your hand and try and explain it to us, I see Azandra has already got their hand up. Now, I see some awesome answers in the chat. What I would always suggest that you do is whenever you're giving an answer, especially if you're giving it as a fraction, always try simplify the fraction that you give as your answer. Right, Bridget, yes, if it's the whole square, so basically of that whole yellow square that I've circled, what is the area of the whole square? I'm liking what I'm seeing so far. Zandra, do you want to help us out?
Ma'am, I think it's half the square because if you add the two small squares together, that will make a half and that will go towards the other diagonal half.
Okay, cool. So if we sort of consider, as Zandra said here, each of the four smaller squares, so square 1, 2, 3, 4 here. I don't know why I decided to number it like that, but I did. So in the smaller square 1, that diagonal, now this takes us back to properties of squares. A diagonal cuts a square exactly in half. So this is half or shaded half of that square. This is obviously the full square shaded. If we then go to block number 4, this is divided into quarters. So we've got a quarter shaded in each case, but there's 2 quarters, which is actually a half. So in this fourth block here, we've got a half shaded, we've got another half shaded. And even though this is a full block shaded, there's nothing shaded in block 3. So if we sort of thought about it, if there was a half there and a half there that would make up the whole, there's actually only a half of the full square shaded in. And so, excuse me, understanding the properties of squares, understanding, I suppose, what an area is, and just looking very carefully at our diagram, we can see that it is only half shaded. Now, a lot of you put in 2/4, simplified as a half. There was 1 decimal of 0.5, which I'm absolutely happy with. 4/8 is also a half, so that's cool. So 2/4, 4/8, a half, that's what we're looking for over here. Palady, do you want to add to it? Or were you going to say a half?
No, ma'am, I don't want to add anything.
Cool, no problem. I just saw your hand was up. Alrighty. So that is sort of a brain break to give you an idea. It'll be different every time. I do try and get creative, but sometimes I can only get so creative. But very nicely done. And just, I don't know how many of you do maths Olympiads at your school. This, if I remember correctly, is actually a math Olympiad question that I took from a past paper. And so these are really good problem solving types of questions to be practicing, which is why I put them up here, because problem solving is sometimes something that we think we can't do, but actually, as you've just proven, you can do it. All right. So let us get back into this whole number system vibe. So I'm hoping we all took our screenshots of what the number system is. Whoopsie daisies. And you can see here that I've got a table and I've got 6 different numbers, and we want to put them into the correct group. So we want to tick the column that applies. Now, guys, we can tick more than one column. It's absolutely fine. And this is maybe also a point where you want to take a screenshot of the table so that you have it to refer back to, or you might want to wait until we filled it in. I'm going to do the first one with you, and then I'm going to ask people to help me out with the next ones. So if we start with the first one, we've got the number 6. Now, if we think about 6, we know that 6 is a counting number. It's 1, 2, 3, 4, 5, 6. So we know that it is a natural number. Now, remember the symbol for natural numbers was this N here. I'm actually just going to write it in here so that we don't forget. Z was integers. Q was rational, and the Q with a dash was irrational. Okay, so we know that this is a natural number. We also know that because it is a positive whole number, it is an integer. If we go back up to this diagram, because it is a whole number, a natural number and an integer, and because both of those fall into the blue block of rational numbers, 6 also then has to be a rational number. So that's essentially what we want to do here. Wamkele, you are welcome to draw it if you really want to, but like, your guys English, but like Elisa has just said, I would just take a screenshot. Obviously, if you want to do it, maybe just draw a rough table. You can always do it neater later on. Or if you want and you don't want to draw the table, maybe list the numbers for yourself and then just put the symbols next to it. So N, Z, Q, so that you have classified them for yourself. So you don't have to draw the table. Okay, so guys, let's have a look at the second one. So B is 2/3. So someone, maybe if they want to raise their hand or if you want to put it in the chat, I want you to tell me which of those 4 categories 2/3 would fall in. It can fall into all of them. It can fall into none of them. It can fall into one of them. It can fall into 2 of them, 3 of them, whatever. But what does it fall into? Okay, if we've got a number here, so let me know what your, oh no, we don't. Never mind. Have a think. Maybe you're welcome to put it in on the chat. Right, 3551886. Please let me know what your name is firstly, and then let me know what you think.
Hello.
Can you hear us? Yes, okay, there we go.
Rational number.
Say it again, it's a?
Rational.
Okay, so it's a rational number. I agree with you because we can write it as a fraction. Excellent. What is your name before we carry on?
My name is Zoe.
Bongi.
Zoe.
You're a bit fuzzy. I can't quite hear you. Can you maybe just put your name in the chat just so that we know for future? I don't want to have to call you 3551886.
Hey, man.
Ah, there we go. Zoe, thank you. Right. Right. So as Zoe has told us, this is a rational number. It is a rational number because I can write it as a fraction. 2/3, if you wanted to, don't know why, I hate decimals. 2/3 is 0,6 recurring. So we could have it as a decimal, but we can write it as a fraction, which means it's rational. Very well done. I saw a lot of you put that in the chat. Excellent. Right, next one. Question C, we have got -4. So have a think. Is it a natural number, an integer, a rational number, an irrational number? And remember, it can be more than one. It doesn't have to only be one. Right, lots of you are saying integer. So let's put the tick in for now. Zoe, tell me.
It is integer and a rational.
Excellent, well done. So guys, remember, if we just go back up to our diagram, the second we have an integer, a whole number, and or a natural number. They automatically are all rational numbers because they fall into that cup or that whole group of rational numbers. So because this is an integer, it is automatically also a rational number. This can be written as a fraction of -4/1. We generally wouldn't because why? But we can. All right, so the second we can write it as a fraction, we have a rational number. Excellent, guys. Very nicely done. So the next one, firstly, quickly put it in the chat there. what is that? What is D? Because that ain't a number, not how it just looks here, but what does that represent? Wonderful. This is pi. Okay, I appreciate the sure, my English there. The pi idea of it's a pi. Okay, so guys, pi, and you don't have to know this, is basically the ratio of a circle's circumference to a diameter. So pi has a lot to do with circles. And if you're going to carry on with maths, just embrace it now. Circles are going to become an important part of your life. So pi, very, very important. Now, pi, I don't know how many of you know anything about pi, but pi is a number that is infinite. It never ends. The decimal places never go on. People hold competitions to try and remember pi decimals. I'm trying to find out for you how many decimals people have memorized. It's something crazy. The unofficial world record is someone holding or someone remembering 100,000 decimals of pi, taking him 16 hours to recite all of those, which is just crazy. So pi just goes. Now, because pi just keeps on going, it never ends. If we quickly go back up to our definitions here, remember we said that if we have a decimal, let's maybe try color code a little bit here. If we have a decimal that never ends, it is a irrational number. Now, yes, pi you can round off to 3,14, 3,146. Sometimes we write pi as 22/7, but that is a rounded value. And so pi is actually an irrational number because the exponent, the decimal just keeps on going. It never stops. So we've got an irrational number. Now, the reason I'm putting this in for you is because often when we test irrational numbers, pi comes up. So it's just important to bear in mind that whenever you see that pi symbol, we might write it differently. So I might give you something like 3 pi or 4 pi or whatever. But if you see pi, it is automatically irrational because of the properties of its decimal. Okay, the last two. My suggestion is if you have a calculator, I would maybe type these into the calculator to make sure that you are working with the most simplified version of it. But with our first one in E, we've got the square root of, Zoe is on it tonight. Okay, Zoe, tell me.
The square root of 4 is a natural number, integer, and rational.
Fantastic, because the square root of 4 is
2.
Well done. So square root of 4 is 2, which means that it is a natural number, an integer, and a rational number. Now, guys, as you can see, as we've gone through this, there's nowhere where I've ticked rational and irrational. That's because if you can write it as a fraction, it means that you obviously can't not write it as a fraction. So you will never tick both rational and irrational, just as a little side note here. Okay, the last one, square root of 5. So take a second. If you're struggling a little bit, put it in on your calculator, see what your calculator gives you. If the decimal doesn't end, if it's just a random decimal, and I'm pretty sure I actually use this as an example, think about what that means. Kia, what do you think?
Ma'am, I think it's irrational.
Fantastic. Well done. So for the last one, this is irrational. Now to just show you, I'm going to put my camera back on. If we put in the square root of 5 on our calculator, remember I used this as an example. example, it just gives us this whole long decimal. There's no pattern to the decimal, so nothing recurs, nothing repeats. Obviously, your calculator can't go on for infinity, but when you see this whole long number, it means that it's probably never going to end. And because your calculator doesn't give it to you as a fraction, it can't be written as your fraction because your calculator's default is to put it as a fraction. And so it means it's irrational. If it's irrational, it obviously can't be natural integer or a rational number. Right, this is one way that we really like to test the number system, giving you a list of numbers and asking you to either tick or state what type of number it is. So this is a good idea of how you could be assessed on this. I'm just waiting here in case anyone wants to take a screenshot. Okay, I'm hoping we've all got our screenshots. Right, I think we'll finish off with this example and then we'll see. So this is another way we like to ask you these questions. And I'm really just showing you these because these are nice, easy marks that we can get. So you've been given the following list of numbers. I'm just going to make this a bit bigger so that we can see. 3, 4, 2. Now, guys, what's really important is that these two little dots on top of the decimal there means that the decimal just keeps repeating. That's what those dots mean. It means it's recurring. Negative square root 25. Now, we know that the square root of 25 is 5. So what we're actually working with is negative 5 here. We've got that pi again. We've got 3 over 4. We've got 2. We've got 0,45 and we've got 0. Now this 0,45 we could write as a fraction as 45 over 100. Remember, when there's 2 decimal places after the comma, it means that we're working with hundredths of a unit, and so we can put it over 100. So now that we know what numbers we're working with, let's see if we can answer these questions. So we can use numbers more than once as we go along, but I want someone to tell me from that list of numbers, which is a whole number that is not a natural number. So think about what your natural numbers are. Think about what your whole numbers are. Which is not a natural number, but is a whole number? Kia, what do you think?
Ma'am, is 0.
Excellent. Well done. So remember, because we have those difficult mathematicians, they created a whole new category for just 0. So 0 is not part of the natural numbers, but it is a whole number. Very nice. Asante, do you want to try? I just muted myself. Right, our next one. An integer that is not a whole number. An integer that is not a whole number. See, Eddie sent me a message with a fantastic answer. Very nice. Think about what your whole numbers are. Think about what your integers are. We want one that is an integer, but not a whole number. Remember, whole numbers go 0, 1, 2, 3, 4, and so they keep going. Integers from negative infinity, so -3, -2, -1, 0, 1, 2, all the way up to positive infinity. So think about that. Which one is an integer but not a natural number? Not a whole number, sorry. Zoe, do you want to tell us?
Ma'am, I'm not sure, but I think it's 0.
Okay, so let's have a look here. If we said 0, basically what we want to check for is that 0 is in the integer line, but not in the whole number line. So 0 definitely is in the integer line, but it's also in the whole number line. So it's actually both. So we want a number that is only in the integer section, not in the whole number section. So far, Zodwa and Eddie are on it. So if maybe one of you want to raise your hand. No takers. Okay, so guys, if we have a look here, our integers are negatives. They include the negatives. And the only negative value I have here is that negative square root 25. So I'm going to stop there. Paledi, do you want to carry on for me? Okay. So guys, as you've got that there in the chat, the negative number, we know that -5 is part of these integers. -5, however, is not part of the whole numbers. And so -5 is an integer, but it is not a whole number. So that is the number we are looking for there. Right, let's do one more. So last one, a number that is a real number, but that is not rational. So basically an irrational number. Which one is irrational? Paledi, want to help us? You guys, last one. A real number that is not rational. So basically, which is irrational? Not rational basically means it has to be irrational. Zoe?
Ma'am, is it not pi?
Excellent, well done. So guys, remember we said pi is a really, really common example of irrational numbers. And so what we're looking for there is pi.